So let's take a number line and choose any number you want, and we'll call that number C. And we can approach this number C from the left or the right. Any number you want. We can always approach from the left or the right. And we can do this forever. Any value of x you choose. We can always find a point between x and c. And I did this in the first video where I showed we can take the halfway point. Now I'm using the absolute value sign here to indicate that we can do exactly the same thing from the right. And maybe we choose this next point as C. Well, we can still keep using this. We can always find another point between x and c. And this goes on forever. And this is what we call then x approaching c. Now, previously, with functions, you would just plug some number in. But in essence, we're plugging in all of these values that represent x going to c. We plug all this into the function. And plugging all this into the function is what we get as the limit then. So we plug in all of these values that represent going to c, and then we observe what the function is doing. And we call that the limit. So as we approach c, this process of forever getting closer, we observe then what the function is doing. And that's what the limit is. So there is a big distinction here in what x approaching c and what the limit means. So x approaching c is something we can always do, because no matter what value you choose for c, we can always approach it. No matter what two different numbers you choose for x and c, there are always infinitely many numbers between them. And so what this means is that x approaching c is always guaranteed. Whatever number you choose for c, we can always approach it. And so this is guaranteed, something we can always do. But that's not true for the limit. The limit is not guaranteed to have an output. In that case, we say it does not exist. So how can that be? Well, let's go back to our number line again. And we have our point of interest. Now remember, technically with approaching, we get forever closer to c, but we never become c. So we can technically have a hole here because we never become the number c. We get forever closer to it. And so we have this line. We can be any value on this line except c. But this line doesn't have to be flat. This line could be curved. And on a curved line, we can still approach c from the left and the right. And then what we ask here is then, well, as we approach from the left and the right, what height are we approaching? And that height that we are approaching, L, is the limit. So remember that c is any number you want to choose. So maybe you want to choose c to be over here. Or maybe you want to choose c to be over here. You can choose c wherever you want, and I can create this same picture. And the limit will always exist. Because what the solid line is indicating to us is that no matter what point we choose, the solid line is indicating we can always forever approach that number. So when does the limit fail then? Well, instead of having a solid line like this, we can cause the limit to fail by breaking that line. So now in this case, when we approach from the right and approach from the left, these heights are no longer the same. There's now a difference in these heights. They aren't converging. And so the left side and the right side don't equal, and so the two-sided limit doesn't exist. So if the function is a solid line, then the limit exists. But once we rip apart the function, the limit no longer exists at that point where we tore it apart, because the left and the right won't equal. So we have this scenario then, that two-sided limits will always exist when you have a solid line. If you have a solid line, the two-sided limit exists everywhere on that line, because the line indicates you can always approach whatever number is on that line. So I can pick anywhere. If I pick this point here, I can always approach it forever. If I pick this point over here, it can always be approached forever, because that's what the solid line is indicating. Now, the other case where two-sided limits exist is where you have a hole. So as long as you have a solid line with a hole on it, that also has a two-sided limit. Now remember, the hole fails though if we break this apart. So if we take this right here and lift it up here, then that breaks. So a hole by itself doesn't mean a two-sided limit exists. It has to be a hole on a line. Now, something else that's true for a solid line is that if you have a solid line, the function is everywhere defined. That's how you create a solid line, when you have a function that's everywhere defined. In the case with a hole, however, the function's not defined on a hole. The hole is specifically there because the function has division by zero in it. So what we're going to do is actually take these ideas right here. We're going to get rid of these ideas and look at these ideas right here. And we put this together and we call this continuity. Now, specifically, mathematically, continuity is defined by this first idea here. The function is everywhere defined. And we write that then as our function f, no matter what value of c you put in, the function is defined. So you have your function. If you put your value of c in it and the function is defined, then that's the first property of continuity. The second is introducing this idea. The two-sided limit exists. And there it is. Just straight up write that statement. The two-sided limit exists. And then finally, to bring these two ideas together, we then say that the limit has to equal that function output. And these three things define continuity. Continuity must have all three of these properties. If just one of them fails, then we say this is discontinuous. So you may be thinking to yourself, well, are all three of these things really necessary to define a nice solid line? Well, let's check out this first one. This function is everywhere defined. No matter what value of c you choose, the function has an output. If you choose this value here, here's the function output. This function is everywhere defined. But you can see it's been ripped apart right here, though. And so we say this is discontinuous at c. It's discontinuous at c because the limits are different. However, the function being defined by itself is not enough to give us a solid line. So we need something else. Let's check out the second statement. Is this enough to define a solid line? Well, we've already seen an example where it doesn't, and that's with a hole. So the limit exists everywhere on this function, even at the hole. The limit exists at this hole. But of course, this hole then breaks this up from being a solid line. So the limit existing is not enough to get a nice solid line. And then for the third property here, there's not really a graph to show here, but more of what these are outputting. So we know, just talked about, that the limit, if the limit exists, then we know we either have a solid line or we have a line with a hole in it. If the two-sided limit exists, then we have one of these cases. Now, if the function is everywhere defined, then we know we have a solid line or a line that is broken. If the function's defined, we know we have one of these cases. So to get just a nice solid line, we then demand that these equal. If we demand these equal, then we know we're in this region here where they're both giving us then a solid line. And this is continuity. So for our first question, question 1, at our point of interest, so c equals 4. So right here on the graph, c equals 4. Check out the homework or the lecture work and answer these 3 questions, true or false, on that lecture question 1. So for property 1 here, is the function defined at 4? Well, it is defined right here at the closed circle. So 1 is true. Function is defined at 4. How about the two-sided limit? Does that exist? Well, if we look at the two-sided limit, we can see if we approach from the left, we'll be at this height. And if we approach from the right, we're going to be at this height down here. And these don't equal. So this is false. The two-sided limit does not exist at 4. And now we get into kind of a philosophically strange spot here, because the two-sided limit does not exist. However, the function does exist. So we're saying something that does not exist equals something that exists, which would make this also false. And those are the answers. So how about this? Question 2. Point of interest, C equals 2, right here on the graph. Check out the questions in lecture question 2. So for the first one here, is the function defined at 2? Well, this is an open circle here, so it's not defined here. However, there's a closed circle here, and that is where the function is defined right here at an output of 2. So yes, it's true that the function is defined at 2. So how about the limit? Does the limit exist at 2? Well, as we approach 2, we approach from the left, we'll be down here. And if we approach from the right, we're coming along on this part of the function. And the left and the right will converge right here at this output level, this height of the function at -3. So it's true that the limit exists at 2. The function is also defined at 2. However, the function output is 2, while the limit is -3. These don't equal, and so 3 is false. And so we say this is discontinuous at 2. So there is another way to approach continuity. And so here's our 3 properties again. And that's to know when they fail. So if we look at the first property, that the function has to be defined. Well, when is a function not defined? And a function is undefined when you have division by 0 or the square root of a negative number. If you see one of these things, or both, then the function's not defined. And if the function's not defined, then you know this automatically fails, and thus it's not continuous, it's discontinuous. So in looking for continuity, you look if there's division by 0 or square root of a negative number. Now for property 2, when does this fail? When does the two-sided limit fail? Well, the two-sided limit fails when you rip apart the function. In other words, when the left limit and the right limit don't equal. That's when the two-sided limit fails. It doesn't exist. When the left and the right don't equal. And so that's something else you look for. If you see this happening in your function, then you know it's discontinuous because it's failing property 2. So let's take a look at this. Check out this function. What do you see here? Do you see division by 0? Square root of a negative number? Well, if we look at the denominator here, there's division by 0 if the denominator equals 0. And so we can solve this equation and get our two solutions. So when x is 0 and x is 2, we get division by 0. And division by 0 causes the function to be undefined. And so we know these two places then is where the function's discontinuous. We know it's discontinuous because property 1 fails. The function is not defined at 0 and 2. Thus, it can't be continuous. It fails property 1. So check this out for the third question. Where is this function discontinuous? So I'm being a little tricky with this one because this is the same function we just did. And what did you have to do? You had to factor to find out where the zeros are. So factoring, remember all that factoring you did in algebra? You're going to do some factoring here again, figuring out where these discontinuities are. So 0 and 2 is where this function is discontinuous. Check out this one. So there's no division by 0 here because there's no division, but we do have a square root. Now the square root, you can't take the square root of a negative number. So that means what's under the square root can't be negative. And we can write that mathematically as that what's under the square root has to be greater than or equal to 0. It can't be negative. And then we can solve this inequality. This is the domain of the function. In other words, this is where it's continuous. All the other numbers is where it's discontinuous. And we know it's discontinuous at all these other numbers because property 1 is going to fail. The function is not defined when you're taking the square root of a negative number. So check this out for question 4. Given this piecewise function, and there are the 3 pieces for it right there, where is this function discontinuous? Now, I gave the graph here because I wanted you to see the graph, but I want to focus on the function given and how to deal with piecewise functions and discontinuity. Is you want to determine if these pieces are touching. So this piece right here is not touching this piece here. So we have, here are our 3 pieces. Here's piece 1, piece 2, and piece 3. And we can check that by comparing these conditions. So as x gets closer and closer to -1, it's outputting 8. And you can see that right here. But in the second piece, as x gets closer and closer to -1, well, if we plug -1 in here, we get 0. And you can see that's right down here. So this output as we get closer to -1 is 8. This output as we get closer to -1 is 0. These don't equal, and so we know these pieces aren't touching. And you can see it here graphically then. And so we know it's discontinuous then at -1. Now, if we look at the other condition here between the second and third piece, which is at 3, if we plug 3 into here, we'll get 8. And as we get closer to 3 here, we'll also be at 8. These equal, which means these pieces touch. And you can see that right here. Right at 3, you can see this parabola. Remember, the parabola goes forever like this. These pieces touch right here. And we can determine that by looking just at the function. So this function is discontinuous at -1, and this specifically then fails property 2. The limit, the two-sided limit, does not exist at -1. So in summary, there's only one thing to say: continuity. And that's this lecture.